Concept zero is the most important one, and that is that systems have, given their springiness, right? That's the springiness, or the spring constant in this case, right? And given the inertia, okay, the springiness and the inertia, they have a frequency, a resonant frequency. Okay. Now it turns out it's a little more complicated than that. Some systems will have multiple resonant frequencies because they can vibrate in different ways. But let's not worry about that. Okay. But we'll look at that when we get to like demos and stuff. There's some incredible videos of resonance. Is possibly the most powerful concept that you're going to learn all year. I'm a little bit sad I'm not there to talk about it in person. But anyway, so concept zero is that when you are driving the resonator at its resonant frequency, the amplitude gets big. This is the single most important thing. Okay, is that it's going to go crazy if you drive it at that amplitude. In fact, if there is no damping at all, that is, there's no way for it to lose energy, you can see that this graph here is an asymptote. Here's our natural frequency, and we're driving it here below the natural frequency, above the natural frequency, right? If we drive it right at the natural frequency, and there's no damping, there's no way for it to lose energy, then basically there's just no limit. If you let it run long enough and you keep giving it energy and it can't lose energy, then it will, eventually just, there's no limit to how much energy it can have. Okay. Now, real systems, like, if you're talking about somebody on a swing or something like that, there's, considerable amount of air friction. So most systems, most real systems have some amount of damping. Okay. So this is a graph here showing you the response of this resonator with light damping, with increased damping, with heavy damping. Okay. And when you introduce damping, okay, damping is this concept that there's a force. Let's say here's our equilibrium, right? And let's say we've got some object on here, right? Okay, and let's imagine that this object is, I don't know, say moving out to this point like that, right? Damping is a force that acts opposite the velocity, just like friction, only a lot of damping forces depend on the velocity, so we need like differential equations. And you'll see, so like, basically the force would be some a minus sign times some constant times the velocity. It would be a real simple damping force. And in general, they're more complicated than that. So it's sort of beyond the scope of what we're going to do in IB physics, right? But the damping force is just this force that acts opposite the velocity of this thing, right? As you add damping, what happens is there's lots of things. Well, there's four things that we need to know about these graphs, right? Okay. The first is that the peak gets lower. So as you increase damping, here's light damping, here's increased damping, here's like a lot of damping, right? Too much damping. Okay, the peak goes lower. So and this makes sense, right? You're giving it energy at a certain rate. If it's losing energy, the faster it loses energy, the lower that maximum peak is, right? Because that peak represents sort of an equilibrium between input of energy and dissipation of energy, right? And when that equals, it comes to equilibrium. It reaches some maximum amplitude, okay? The other thing that happens slightly is that the frequency actually decreases. So say it's resonating at 5 hertz, right? With increased damping, it might resonate at, say, 4.8 hertz or 4 hertz. There's a slight shift to the left. So these peaks, notice that they're shifting a little bit to the left, okay? They also get broader. So with light damping, it's a fairly specific thing. It tunes in and it's got a sharp peak like that. With more damping, the peak gets broader. In fact, here we can't even really see that there is a peak, right? And then also, the other thing that they like to talk about is at the extremes, like here, right? And then out here, presumably, these all come together. So at the extremes, these things are the same. So those are 4 things about these types of graphs. As you increase the damping, the peak gets lower. It also shifts slightly to the left. It gets broader. But at the extremes, it's about the same. Okay, so let's look at some other graphs here. Let's see if that's true. Okay. Indeed, so this is the envelope, right? This is the resonant thing without any damping. That's the red. Okay. Notice that as we increase, and this must be some sort of a damping factor. Okay. As you increase the damping, this peak gets lower and lower and lower and lower. So it gets lower. Okay. It gets broader. Notice that this peak is getting broader. Here it's nice and spiky. Here it's pretty broad, right? Okay. It also shifts slightly to the left, right? And then if you notice, they've got this plot of where the maximum occurs, right? So this is, this must be something that they do in like differential equations or engineering, right? So it shifts to the left, okay? And then notice at the extremes that the behavior is the same, okay? Same at the extremes. Okay, so and they'll ask you to draw these graphs. So I don't know, we should practice that, I suppose. Here's another one again. Just repeat that, right? As we increase the damping, right, the peak gets lower and broader. Right, more damping, right? It also shifts left. This is true about the peak, right? Okay, and then notice at the extremes, the behavior is the same. Extremes are the same. All right. Yeah. All right.